as an expert in the field of near-field cosmology. And that is part of what he got involved in Maunakea's Spectroscopic Explorer project, where he is now the project scientist for that project. So I'm looking forward to hearing what he has to say about both of those subjects.
Well, thank you very much, Jennifer. And thank you, everybody, for attending, particularly this week of Thanksgiving. I'm sure many of you will be getting on planes fairly soon to go to various places or whatever. So thank you for taking the time. Yes, so as Jennifer said, I'm going to speak today mostly in my capacity as a project scientist for this telescope, half of which you might already recognize as something that exists. And the view sort of gives it away in a sort of spectacular, only slightly photoshopped image. However, my background, though I do a lot of work now with instrumentation teams and instrumentation development, my background is very much not instrumentation in terms of what my PhD was and things like this. So I thought this potentially would help you a little bit understand why I'm excited about this if I explain a little bit about what it is I actually do in most of the rest of my life. You always start with a movie, and this movie, which has volume. This is a great song, but it may be mildly inappropriate, so I'm not entirely sure how to... Oh, there we go, awesome. I can show you the unedited version later. This is a fairly nice movie that was made many years ago, so those of you who work on nearby galaxies will recognize this, of course, as the Milky Way and M31, and a whole bunch of galaxies surrounding it, except this is now vastly out of date. The number of galaxies here is now, well, I won't say it's more than doubled since this was made, but there's been at least another 20 or 30 additions to this. And so this is a fly-through of the local group, the Milky Way, M31, M33, HC205, M32, up there you have some other dwarf ellipticals. And this is a great playground. It's a playground for, I think, many people in this room. And it's a great playground for astronomy right now. In terms of these are the galaxies for which we will, this works great with music that's spinning around. This is a great arena. These are the galaxies for which we'll basically always know the most information in terms of we're going to be able to get the most detailed view of what it is they look like, what are the stars doing. And from that, we can start piecing together how it was that they actually formed, what it is they actually look like, what are their dynamical properties into dark matter, the ancient dark matter, and things like this. So this is a wonderful playground. And it's a playground for which we have a lot of information. Okay, we have wide field imaging surveys. People here are probably involved in dark energy survey, but lots of others as well, NCSS, there'll be LSST in the future. And you also now have an awful lot of great astrometry stuff. So this is the Milky Way, as it will be looking like when you look into the sky in the future, with all the stars buzzing around, because we're starting to measure all of the proper motions of all of the stars that Gaia can see, about roughly 5/20th magnitude thereabouts. And so we will know the colors of these stars from the imaging. We will know many things about how they're moving on the plane of the sky. But what about velocities? Well, velocities, of course, we get via spectroscopy, right? And many people here are involved, in fact, in building many of the next generation spectrographs. But this, this view of the Milky Way covers the entirety of the sky. Okay, M31, as a fairly nearby galaxy, to actually look at it in its entirety, you're actually covering a very, very large area. This is M31 there, M33 roughly to scale. Projected distances of about 150 and 50 kiloparsecs surrounding these galaxies. And this is a megacam survey called PANDAS, picture of all of the stars in the vicinity of these galaxies, right? So these two galaxies are 15 degrees apart in the sky. Okay, PANDAS, when you haven't filtered it, has something like about 15 or 16 million stars in it, above some magnitude limit for which you can then filter down and look at these various things. Now, many of these features that you see are, enormously long tidal streams, many, many degrees across in the sky, the sorts of things as well you can see in the Milky Way. Trying to understand the structure of the Milky Way is in some ways easier insofar as you have access to more information, and is in many ways harder, because we are right within the Milky Way trying to figure out what it is we're actually looking at. Okay, so we have all the projection issues. Here you sort of have a Google map of the galaxy, right? And you can then sort of look at all the different features. And you can look at all these features, and you can sort of, draw pictures around them, and you can include the blobs, and blobs of dwarf galaxies, and blue blobs of dwarf galaxies, red are globular clusters, for example, and then some of the major features that you can see are outlined here, and you can say, well, this is what a galaxy looks like, an L-star galaxy halo out to about half of its very radius. This is the stuff that's in it. Great. But what does that tell us, right? And so then trying to figure out actually how do all of these things connect together. It's hard, and this is just projected spatial information, right? So you can do various things, and I'm not going to go into this. But you can actually start trying to figure out mapping how all of the different structures fit into one another. And you can start trying to figure out all of the connections between the different substructures and how you do that. But this is just, in my case here, it's just projected spatial information. It's an X and a Y coordinate. Okay, the Z coordinates is more or less everything's at the same distance. Okay, but what about all of those other parameters we can have, all of the kinematic information? Imagine for not just MK1, not just the Milky Way, you have enormous amounts of velocity information, including the radial velocity components. Turns out you'll probably have a lot more tangential velocity components because of Gaia doesn't know radial velocities. So what about being able to convert it to velocity fields to actually start looking at the entire hemodynamics, the chemistry of all of those stars, to actually deconstruct this galaxy into its building blocks? And that's exactly what we're trying to do with the Milky Way as well. But remember, with the Milky Way, we have the challenge of essentially having to map the entirety of the sky and get velocities of what is now literally billions of stars that Gaia can observe, and for which 4-meter class spectrographs will be getting millions, which is great, but it's actually still just the brightest subset of those as well. So it's with that in mind that I started getting interested in, okay, let's figure out what it is we actually want. But regardless of where your interests lie, maybe you are building stuff for the GMT, maybe. Or maybe you're involved in LSST, maybe. Or whatever, right? You could be involved in Euclid, you could be using Gaia data. Canada, we're heavily involved in TMT. If you're European, you like that one there. W first, maybe you're doing radio stuff, maybe it's SKA, maybe it'll be NGVLA in the future. You're going to have a huge number of sources for which you don't necessarily have redshifts, potentially, if you're detecting H1 continuum or whatever. So you want to get the optical spectroscopy. LSST, SCSS is massively successful, and SCSS is massively successful because of its imaging plus spectroscopy. LSST is going to be phenomenal in terms of the imaging. Where does the spectroscopy come from? How do you select the smallish field? I mean, the GMT had a decent field of view, right? But it's 20 arc minutes or something like that. Okay, which 20 arc minutes of the sky do you want to be looking at? How do you actually then sort of filter down all of the things which you can map with this to the things that you want to follow up with this? I would argue that there's a step missing. I would argue the thing that is missing is massively multiplexed spectroscopy on a big, so here we're talking about 10, 11 meter class telescope. Of course, we're very familiar with this science with 2 meter class telescopes, SCSS. We're becoming familiar with this science 4 meter class telescopes with DESI in the near future. And if you're European, you also have foremost, you have Weave. But you don't have, it's on a 10 meter. The sorts of things you could be doing, right? So if you think of the Gaia science, then things like DESI, foremost Weave, DESI, Hermes, all of these things. Certainly at higher resolution, you can be going down to 16 magnitude very well. At lower resolution, you can also push down to here. Lower resolution, probably not going to be doing as much chemical abundances. And this is just basically a map of what sort of magnitude you need to get to and what sort of distance out in the galaxy you're going to be probing, depending upon the sort of thing that you're looking at. So if you're wanting to trace, for example, bright giants, so horizontal branch stars, red giant branch stars, if you can get down to sort of 16th magnitude, then you're going to be doing a lot of great spectroscopy, a lot of detailed dynamics, potentially chemistry as well, for things in the outer disk, the outskirts of the Milky Way, as we generally understand it. But if you're wanting to push into the halo, even with those bright tracers, you need to be getting down to much closer to sort of the limits of Gaia. And turn-off dwarfs, far more numerous once you get down to the dwarfs. There, And so that's sort of what's been built up your massive statistics, your kind example statistics. There you're not getting even as far as that. So again, if you really want to start probing the halo in situ, for example, the outskirts of the galaxy, in the outskirts of the galaxy, rather than those stars which usually belong to the outskirts of the galaxy but seem to be passing close to us at this moment, then you want to be looking at 10-meter class science. And this is well understood. Again, a lot of the 10-meter class science we're doing, right? We're doing with things like Keck or whatever, but those are hundreds of stars in small fields. What we're talking about here is essentially industrial scale science, much of which people here will be very, very familiar with. The sort of information that's available with this is just a simple synthesis of I think it's a red giant branch star, just showing the optical spectrum. The sort of baseline at the moment, the design we have for the high resolution spectrograph, you're looking at sort of 40,000 resolution, or 40,000 towards the bluest end, an hour of 20,000 once you get out here. The reason for that is there's an immense amount of information in the blue and the UV, a huge number of very weak lines, very important tracer elements, but it's also very crowded in the weak lines. So you need the very high resolution to really go down there. Once you get out here, you still need high resolution, but not as high. These sort of just show you zoom-ins of the sort of stuff that you could get. In the blue arm, just to show you kind of information, this is a tiny little strip of light that NRC might be looking at any one time. Again, the position of these windows can change. But that tiny little strip of light gives you this spectrum. And just to blow up this tiny little bit of this tiny little bit gives you all of these different nucleosynthetic tracer elements that you can be studying. Okay, and again, what you need an hour of 40,000 to be able to really get in and do that science. And you're doing that for potentially all stars and all components of the galaxy. Dwarf galaxies. Dwarf galaxies are cool. I'm not going to try to convince people here that they're cool. I think people here know that they're cool, or have been told that they're cool by some of their colleagues. So this is a dwarf galaxy that's very cool. This is NEC 6822. So this is 6822 is a couple hundred megaparsecs at least from us. You pull out a map of the stars. This is an outdated map. I'm sure there's a better map now, just so where the stellar distribution is. The H1 is doing something very interesting in this galaxy. 6822 is an interesting beast. But anyway, just dwarf galaxies, small things. However, there's about 2,500 stars in this galaxy alone, which are very bright. There's about 8,000 stars just in the top, half magnitude, so just the top little slice of stars, mostly what's plotted here. In fact, there's about 8,000 stars for which, if you had a 10-meter class telescope, you could easily get, or you can easily get to this, but there's about 8,000 stars to choose from. And then if you're going down to just within a few magnitudes of that, you've got something like actually more like tens of thousands of stars. If you're looking at just the youngest populations alone, you're looking at populations of thousands of stars spread over, a couple of degrees. And that's a very hard observation to make with current instrumentation. Okay? This is not the sort of program you can imagine getting kinematics and chemistry for literally every single star in this galaxy, down to several magnitudes. Painted in the red giant branch, probing a whole bunch of different ages of cell populations, a whole bunch of different chemical evolutionary histories. And that didn't take you that long if you had a really huge telescope, just doing spectroscopy. But it's not something that can be done right now. People are trying to sort of incrementally go there, but you can't. And sort of science you can do, I always hesitate to talk to you about dark matter any time we leave the room, but I'm going to try. Matt Walker read this, right? So what do you think? Okay, but this is a simulation of what the true dark matter density profile of the galaxy happens to look like. And this is what you measure for the line of sight velocity dispersion. Sort of if you synthesize a whole bunch of observations of if you have 100 stars, that's the sort of green contours that you get. And the implication for what you might be saying about the shape of dark matter density profile is something like what you see here. But if you go from to 1,000, go to tens of thousands of stars, you start actually honing in on the dark matter density profile very, very well. Add into that a whole bunch of things that currently really get me. Binary stars, right? People don't, people are not thinking about binary stars. I can see some papers. But in order to do these kinds of things properly, you're looking not just at getting a future amounts of velocities for stars, but repeat observations to get rid of things like binaries. In terms of the outskirts here, where you're actually trying to distinguish between what is a member and what just happens to be in the vicinity. again, that's very hard to do, and again, that's the whole gravitational potentials, potentially really interesting dynamical probes are out there. So this is why you want very large data sets of dark matter halos on all scale. NGC 6822 is a bright galaxy, but there's now, of course, huge numbers of faint things as well. Some people like to look at galaxies where you can't see stars, which is fine. They've made their own sort of choice. And so here, for example, are some of the things that you can be talking about. This, I love this science program, actually. First of all, this shows the star formation history of the universe as a function of look back time, so the peak of the star formation history here. And this shows essentially the wavelength range of MSE, but specifically it shows you what the observed wavelength of O2 is as things get redshifted further and further back. So as you move further away, things are more redshifted. And so something like O2, which is a great tracer of various properties of star formation that's occurring in the galaxy, that gets redshifted from 400 nanometers out here out to 1.8 microns. Therefore, to actually look at galaxies as a function of redshift out to beyond the peak of the star formation history of the universe using the same tracers requires very broad wavelength range, but it also requires very large apertures. So this is a science program which is developed, which has changed slightly now. But each of these survey tubes is photometrically redshift pre-selected. Okay, so you have a rough idea of where you are in redshift space before you actually look at these galaxies. Each of these things is the size of the Sloan Digital Sky Survey Legacy Survey, right? And you're doing 7, 8, or 9 of them as a function of redshift out to beyond the peak of star formation history of the universe. At all points, you're getting down to a depth below the M star, the typical mass of a galaxy, and then beyond that, you're still probing down to fairly low mass galaxies, out to the formation epochs of the very first galaxies, the very first massive black holes, and things like this. So again, you're talking about doing Sloans as a function of redshift, not just by themselves. Things like time domain, reverberation mapping, if you're wanting to look at the growth of black holes, how do you do it? This doesn't use the full multiplexing of what you might want for NRC, but here, reverberation mapping is a wonderful technique, whereby you're essentially looking for time delays between the variation in broad and narrow line regions of AGN. This tells you about the dynamics of material very close to the black hole. It's a way of measuring masses of black holes, but more importantly, in some respects more importantly, you're also probing the growth of the black hole. You're probing the energetics of radar formation at particularly active times. Here you can imagine taking hundreds of observations of literally thousands of black hole of ADNs, like black holes, again, out to beyond the peak of the star formation history of the universe. These are 5, 6, 7-year observing campaigns with all of the different observations spaced sort of what we're looking for in time, to probe the different time scales that are relevant. They completely dwarf what is possible today, but you need highly stable, highly accurate spectrographs. You need to have incredibly good calibration, spectrophotometry as well, because you're measuring fluxes in very specific regions over very long time scales, so you need to be going back and back. So these are things which actually don't favor an instrument that's moving on and off a telescope. You may have calibration issues anytime you make things change. You want a highly stable system. Or maybe you're doing some other kind of time domain. Time domain is, of course, growing all the time, and time domain spectroscopy is a hugely exciting area. You can imagine doing a lot of repeat observations. This is where you actually see the emergence of broad line absorption in the quasar, which previously was fairly not unnotable. And then over time, you actually see this broad feature emerge. That's just one example. The point is, with data sets, with the telescope, that is only ever doing spectroscopy, which is literally every night. Every observation getting 4,000 or 5,000 galaxies or stars or whatever, and you're using that every night for a decade, longer than a decade. The sort of science that you can do really is quite spectacular. And so that's what's really driven the NRC science development to date. The project, I'll get back to some of the timeline later on. But essentially in 2015, the then science team was charged with developing not just the science space, but also a set of observations that would be uniquely possible, uniquely transformational. Transformational is a word I actually feel dirty using it. Because everybody's transformation fixated. This really is transformational. But it's something that would be uniquely transformational and for which basically you cannot do unless something like MSE is built. There's obviously a tremendous amount of science that you would be able to do better, more efficiently, blah, 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 blah. That's not why you build an entirely new facility, an entirely new science project. It's to do something completely new. And so those were became the science reference observations. Things like SDSS as a functional bridge, things like the AGM Reverberation Mapping campaign. They formed a key part of the detailed science case. The detailed science case version 1 has been available on the web since about 2015, maybe early 2016. And as appendices to that is all the science reference observations, which have been key to understanding the sort of what it is we want to build. There's, however, now a science redux. In March of this year, we put out a call for new members of the MSc science team. The MSc science team grew from 100 members to 336 members. More than 200 people joined in the last 6 months, which is wonderful, in 31 countries, which blew my mind when I counted that up. And something interesting happened.
Close the presentation button on there.
Oh, I think we have just pressed close the presentation. Is there a presentation button? Awesome. Okay, 336 is strongest. Okay, and so then essentially because so many new people joined the project, which is just wonderful, and because when we wrote the science case, Gaia was not launched. Okay, Gaia is setting the agenda for emerging near-field multi-cell and Milky Way science for the next many decades. It hadn't launched by the time we wrote the science case with Spectrographs. Gravitational waves, very cool, hadn't been discovered. Okay, that obviously has a big impact on a lot of time domain high energy type of stuff. And as well, there's lots of strategic planning exercise underway. Decadal plan here in the US and Canada, we have a thing called the long range plan, which I'm sure all of you are always keen to hear about. And there's other exercises as well. So we thought the time is right to actually go and revisit the whole science case as well to sort of, enhance the science case where we can. So the way we've done it this time around is a little bit different. There's now 8 science working groups charged with revisiting the MSc science case. And essentially they're going to be laying the groundwork for the design reference circuits. Because you talk about science cases, and the SROs, the science reference observations we use, were kind of like detailed observing proposals. But what we're going to be needing in the very near future is actually mapping a lot of the science into actual surveys to actually sort of demonstrate this is the science we're going to get. And from the development perspective, from the engineering perspective, those sorts of things are very important as well. So we formed these science working groups, which are firstly revisiting the science, and then we'll get into the whole design reference surveys, which we may talk about later. There's 8 different groups. At the moment, these are not supposed to be bins where nobody talks to each other, but rather just organizational structures. And so it's really, I think there's going to be a lot of incredibly interesting science coming out of this. Some of the ones I'm most particularly excited about is a lot of the stuff on exoplanets. We're not going to be exoplanets, of course, we're not a precision with the velocity spectrograph. But in terms of a huge amount of stuff to do with post-characterization and actually understanding the large statistical populations of planet-hosting stars and such like, I think this is going to be very exciting. And particularly Daniel Huber has managed to recruit what seems to be like most of the fatal team and others into this, so that's going to be very exciting. Obviously, Milky Way resolved cell populations is great. Lee is in charge with Aaron of refocusing the galaxy formation evolution science working group. I mean, that's a huge science working group that they're in charge of there. Astrophysics Professor Dark Matter, this is one that really I think I'm very excited about. And a lot of the inspiration for this was actually a presentation that Tim gave at Snowpack, where basically she was talking about all the different ways there are to probe dark matter astrophysically. And so then basically the idea came, well, let's not just talk about all these things independently, let's actually create the suite of connected observations that together can really start honing in on the properties of the dark matter particle, and really start distinguishing between these sort of things. So Harv and Coach are working on that. And the cosmology group as well is going to be very interesting. Obviously, cosmology is usually a major driver for things like MSc, in terms of white hole spectra, just DESI or EFX. Right? When we came along, MSc's timing has historically sucked, right? In terms of the fact that Many of the cosmologists, when we were doing this the first time, were still preoccupied with trying to figure out LSST and Euclid and W first and DESI. Whereas now, those same people, even though those projects are kind of about to start, they're rightly thinking, well, what's next? And so we've got a couple, well, in fact, these are just the leads, right? So we've got a large group now of all of these people who are now actually thinking about, well, what comes after DESI, what comes after PFS? And by all accounts, I haven't seen the work that they're doing, but they're telling me that we have something that is highly competitive and very interesting. Neutrino masses were mentioned. It'll be interesting to see what comes up there. Okay, so based on the science reference observations that we had, we developed a whole bunch of different science requirements, and we tried to go fairly light on this. Interesting to ask Jennifer and Aaron, etc., about what people mean by science requirements. Our way around with this was to have as few as possible, to really just focus on the key capabilities and have the traceability, whereby if something is boxed in red, it means that this set of observations actually define the requirement. If it's green, dark green, it's very important to the requirement. If it's light green, it's somewhat important, and if it's gray, it's not important at all. So we basically have a way of figuring out what's important and what's not. And how you interpret this, obviously, is always a key thing. But again, we have very good traceability right back to science. Science drives everything, even though the concept is well known, the specific requirements have a very clear origin. And so this is what we are, the sort of table of capabilities. Let me just click through there so you can really see all of them. We are going to be situated on Maunakea, which is a latitude of 19 degrees, which means you can see more than half of the southern sky, so 3/4 of the entire sky. That's not obviously a science requirement, that's just a fact of life. The aperture is 11.25 meters. I'll come onto that in a little bit. This is obviously a very large telescope, larger than Keck and others. In fact, if you, other than the GMT, ELT, TMT, it's the biggest. So as I like to say, if you ignore all the telescopes that are bigger than MSC, MSC is the biggest telescope. And if that doesn't win you over, right? But so we're large. And the reason for that is sensitivity, right? So again, this is all traceable. The field of view is 1.5 square degrees. And you can be doing observations at low, and by low we mean about our 3,000 resolution, moderate resolution as well, of more like 7,000, and high resolution going up to our 40,000 in the blue. The number of fibers that you have doing that, galaxies have faint galaxies have very, very high space density, the sorts of things you can see within 11 meter, and really you want to be as close to 1 fiber per square arc as you can be. That's technically really hard, so that's like 5,000 something, which you ideally like. But we're pushing this as hard as we can, and we've got about 3,200 low resolution fibers in our field of view. At the same time, we have 1,000 high resolution fibers. So these are sort of brightish, still faint by galaxy times, but now like 20th magnitude stars away from the dark nuclei, work out their space density, the sorts of things that you need. And this is very close to what you really want in about 1,000. So simultaneously, though, those modes are always available because of the way in which we're doing position. I'll talk about that later. Which means every observation you get 4,300 spectra. Okay, that means you basically, if you baseline to an hour observation each time, which is actually probably on the long side, but let's say you're taking an hour observation each time, and you have the length of the average length of night on Maunakea, and you have a good observing efficiency, then that means you do a Sloan Legacy survey worth of spectra every about 7.5 weeks. Okay? And so again, this is a very efficient survey machine. When you're doing that to much, much, much fainter magnitudes. We also want to be IFU capable, that is, say, have a multi-IFU system, because that's the sort of science you can do there as well, is wonderful. However, because of just the challenges of doing this bit, it's been decided that the way in which to deal with this is to make sure that we don't do any decisions that design out an IFU capability, and that we keep that option in. So again, for those of you who are familiar with Sloan keeps reinventing itself every 5 years, right? There's a new set of surveys, but occasionally they actually bring in a completely new instrument as well. Okay, and MSC is going to operate for, I hope, 30, 40, 50 years or something, who knows. And so you want to have the options to be able to do these upgrades. And so this is an obvious one, which we're aware of, and so which we're designing to allow. The bottom line is, if you consider, again, I keep using SCSS because I think that's a good example, right? Consider SCSS, okay? Why was it so successful? Multiple reasons. One, it starts out with this incredibly uniform, homogeneous data product. And the other reason was it just specializes. It specializes. The instrument is very well understood. You go to huge data sets, etc. It's not because it was a big telescope. It's like a 2-meter telescope. And it's not because it's at a great site, because, no disrespect, it's at a kind of crappy site. Okay, and I mean, I don't think that's controversial at all. Okay, so imagine an SCSS type thing, but on a 20 times larger telescope, at actually the best site for astronomy on the planet. Okay, and that's what we're talking about with NRC. So I think it's quite cool. In terms of comparison to other things, well, we'll talk about 4 meters, etc. in a minute, but obviously you're not competing in any way with 4-meter telescopes. 4 meters or 4 meters, and you're 8 meters, and you're sort of in a different set of parameter space. And in terms of things that actually look a bit like this, in terms of being on a large telescope, you have 2 things. Your VLT has this instrument called RUNES, which is, I guess, recommissioning fairly soon. And Subaru has PFS. PFS is essentially like the origin of these 2 projects is kind of traceable to the same sort of set of events, but then you went 2 different ways. And the one which is somewhat, great focused science, but somewhat less capable is PFS, and the one which is considerably more capable is NRC in terms of its grades, in terms of the actual physical capabilities it has. Graphically, this is what they're sort of looking like here. This is the wavelength range that you covered, just to sort of show. These are 4-meter class things. This is PFS, and RUNES are the 8-meter class things. This is Aton Du, which is something which is sometimes useful for sort of discovery efficiency. It's an aperture multiplied by a field of view, so sort of how efficiently can you map the sky. But I think the key comparison is probably in terms of looking at sort of survey speeds, where you have, this is an aperture times a field of view times the number of fibers, the multiplexing. And then this observing time thing, so let me explain that in a second. But essentially, these 3 things just show the survey speed here. Where the observing time comes in just in terms of MSC is always on the telescope, it's 100%. MUNS is always on the telescope, it's 100%. PFS is an instrument. If it was on the telescope 100% of the time, this would be its efficiency. However, if you're thinking about PFS, it's probably going to be doing some focused surveys, which, if it follows the heritage of what Subaru has done in the past, will be about 20% of the available survey time. So the strategic survey programs that Subaru is intended to do with PFS will be the histogram. These plots are kind of great if your favorite telescope shows up, but they're also just kind of made up. It's more what's the science, what's the capabilities. This doesn't take into anything to do with resolutions, or in this particular plot, anything to do with wavelength range. So you should always take these as a grain of salt. But the point is, we're a very efficient thing. There's basically nothing like this in development right now, even although it's recognized that there should be. So facility transformation, this is the novel bit. So that telescope is CFHT, and it's really, if you're Canadian or French, you like CFHT, or they chuck you out of the country. But no, it's a great telescope. Okay, it's older than I am in terms of when it saw first light, but it's been sort of a great facility, mostly actually doing a lot of wide field science, but not just wide field science. The M31 mapping I showed you earlier, that is all CFHT, and it's still quite an active telescope. Now, it's a very old telescope. This means its design is such as a 3.6 meter. This design is such that steel was cheap back in the 70s. So it sits on this big pier, and there's an awful lot of space around it. Now, fun fact is that this 3.6 meter telescope weighs 266 tons, and Keck, a 10 meter telescope, weighs 270 tons. Again, CFHT has an awful lot of steel. So therefore, it's been well known since, well, the story was that basically Canada and France were wondering what to do with CFHT back in like the 90s. And this was before TMT, GMT, ELT, blah, 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 blah. So one of the ideas was, hey, let's put a giant telescope in the CFHT dome, because we can put a bigger telescope in there. So they did those studies, and they actually showed that you could put in the bigger telescope while still keeping the same footprints. the same 3D field, pretty much. But then at that point, some people in Canada were starting to speak to people at Caltech in California, and that's when they joined forces and TNT became a thing. And so then this plan to upgrade CFHT sort of fell by the wayside because there's this new thing to play with, right? But this study had existed for a while, and so it was like, oh, okay, that's interesting. So then, basically, we were sitting around wondering how could we get this set of capabilities, and then we were like, and then one of the older people in the department who'd been involved in this said, well, you can do a bigger telescope with CFHT. I'm like, really? It's, yeah, no, really. So this is now NRC, where everything below this level is the same. You'll notice we've actually taken out the floor, but the pier is exactly the same. There's some structural reinforcement has to be done just to bring it up to modern building codes. But then you obviously have to replace the dome anyway, because you don't have a large enough slit to point the telescope through, right? And so therefore, this dome is just very slightly bigger, 10% in height, as I mentioned. And you've actually got one of the primary sites. This is CFHT is on the very summit of Maunakea. And if you speak to people who know, they'll probably tell you it's actually the best sub-site that was arguably one of the top 1 or 2 sites for optical astronomy on the planet. And this is what it would look like from the outside. Again, everything below this level is the same, but it's a new rotating dome. So we call this the building and the rotating bit the enclosure. Okay, basically that's later on. So that's the idea, and this is what it would be. So it would be a 11.25 meter prime focus telescope with instruments placed on the nascent platform. Yeah, it rotates a few times. So essentially you would have light rods focus up here, which would then be sent down to spectrographs located both on the pseudo-nascent platforms on the side of the telescope and down into the dome, specifically this. So light comes in the collapse enclosure, down of the 11.25 meter telescope, up to the prime focus. Here you have the micro corrector, atmospheric dispersion correction, 4,300 and something fiber positions, feeding 4,300 and something fibers, of which 3,200 go down the side of the telescope to spectrographs located on these platforms. There's no focus here, so these aren't nascent platforms, they're like pseudo-nascent platforms. Where you put the low resolution spectrographs and log their fiber feed down into essentially what we're doing. When you did the high resolution spectrograph, in fact there's 2 high resolution spectrographs, this just shows 1. Where all of this building is more or less the same, and all of this building, all of this part is new. So that is the concept. We are basically trying to, actually, oh, never mind. I had a slide basically just showing how this all breaks down. The key point is we're trying to use existing technologies, existing studies as much as possible in order to actually show that none of this is sort of high risk and new. Because when you think about what we're doing, right, we're building a 10-meter telescope, that's been done. Okay, we're doing wide field spectroscopy, that's been done. Okay, we're doing a high resolution spectrograph, that's been done. There are some very, very interesting things in high resolution spectrographs. Low resolution spectrograph, that's been done. Right? It's the suite of capabilities that has not yet been brought together in a single facility. Okay, so we're not trying to sort of redesign the wheel. It's been this wonderful study of enclosures, you know, what's the best kind of enclosure to do. And we're modeling basically what we're doing on a study motivated a long time ago by the 13-meter telescope. We're sort of independently now with the same company who actually our building is considerably easier, but it's considerably smaller. In terms of the telescope designs, we're doing a prime focus 11 meter. That's not a coincidence. People think, oh, that's the largest telescope you can do or whatever. No, we looked at a whole bunch of different options, including sort of 12 and 13 meter Cassegrain options. This is a sort of pseudo prime focus, a very clever design, but not quite possible. And then these are sort of, because it has to be a segmented mirror telescope once you get to 10 meter and above, the telescope size is not continuous, right? As you need to add rings of segments. So if it's not 11.25 meter, it's 12.4 meter. Okay, it's this sort of way it stands up. And it turns out that the 12.4 meter, you try to do that as a prime, and the speed of your telescope is such that fibers basically can't actually get the light in anymore. So we did a sort of a fool, because we're essentially designing a telescope and an instrumentation suite at the same time. So this allows us to do a whole set of optimizations, which is really cool for people that way inclined, I should say. And so we've looked at this, and so the whole sort of 11 meter pi is not set, for instance. And the fiber system that we're using, we have an interesting set of constraints that really force us to a specific solution. Things like DESI, right? So DESI, and I think SCSS5 actually, I think Police done this design at Ohio State. But they have little motors where each fiber positioner has a little control region that you move around like that, and then you have your, you then have 5,000 of these or whatever in the case of DESI. And that's great if you're doing something which requires 5,000 fibers to cover that area. But if you're doing something which requires 3,000 fibers to cover that area, and also another 1,000 fibers to cover that same area, then that first solution means that if you're using a third of the fibers in one mode, you're only covering a third of the area. Okay, so you actually have a bit of an issue there in terms of how you, so we can't actually use that model just straight up. Turns out that there's a pre-existing fiber positioner out there, which was first used in FMOS on Subaru, which people will point out is not the world's most productive spectrograph. But the concept is very good, which is basically tilted spines. This has the advantage that there's no motors anywhere near the focal length. So this is a very, very passive system. Essentially, these spines can point in what is actually a very, very large control region. And it's because of this very, very large control region that you can actually have 3,000 of them cover with very high density a certain field, but 1,000 of them will still cover that same area as well, such that you then relate it right to the focal plane. The point of this is, what's really great about this as well is you can use both modes simultaneously, which previously was not demanded by us. It was like, this would be great if you could do low and high resolution together. You actually can. So that's a huge increase in observing efficiency. But it does have this issue that we find is tilt slightly, so the light enters the fibers at a slight angle, which is not what you want to do normally. But when you do the analysis, what that means, it's a tiny loss in throughput, which is basically almost negligible with other losses in throughput, but it also modifies your PSF. So for those of you who are instrumentation minded, that's not a great thing. But it's a very calibratable thing. It should be a very calibratable. So that's the trade-off that we need to do with that. The spectrographs, suffice to say, the spectrographs are nothing fundamentally new, except we really are pushing parameter space. We have, in the low resolution mode, we have optical plus J-band plus H-band. That's a huge optical that's a huge wavelength range, including going into the thermal infrared, which produces a huge number of challenges. And the spectrograph, low resolution spectrograph alone is about $17 million. It's a huge package, which I doubt one place will do, but there's obviously a huge number of collaborative opportunities there for different parts. The high resolution spectrograph is awesome. By awesome, I mean almost physically impossible, which is great, right? Insofar as spectrograph size is scaled with telescope size, right? With your inference aperture. And unfortunately, once you're at an 11 meter, that's quite a large number, you're constrained by the size of optics, etc., that exist. And so this then actually forces you into a very physically large grating. By physically large, we're talking the biggest grating that's ever been made is about, I think it's 900 nanometers, and it was for Hermes, though maybe Apogee is up there as well, I'm not sure. Ours is about twice that size, with a line density that's about 50% higher. So you have about more than 6,000 lines per millimeter in this high resolution spectrum. To get to our 40,000 on an 11 meter, and you have 1,000 objects. So that set of parameter space really pushes you into something that's very interesting. And so we're starting to do some prototype testing. So if I say the science instruments are epic, they're challenging, but they're not actually outside the realms of what is feasible, but there are some really interesting things there for groups. So this is sort of how the whole thing breaks down. We all love looking at these diagrams, obviously. This is, the observatory building. The observatory building is the thing that doesn't rotate. The enclosure is the thing that rotates. Everything to do with the telescope, and it supports the science instrument package, everything to do with the spectrographs and the calibration and things like this. OASA, which is all the software, the observatory execution software, which lets the telescope and instruments talk to each other, and PESA, which is the program execution software. And so PESA is just kind of an interesting thing by itself, because you're looking at something which is basically doing a Sloan legacy survey every 7 weeks, right? In terms of the sheer number of targets that you have, how do you actually schedule such a thing? How do you figure out what you should be doing when the only thing we can do is spectroscopy? Okay, so if the seeding goes to crap, you still have to find something to put down these 1 arc-second fibers. So how do you sort of dynamically manage a system like that and execute all these things? So the whole front end of MSc is a fascinating challenge. The back end is also super important, of course, when how the data gets calibrated and served out. But it's also something which is more familiar, right, from things like SCSS and such like. The bottom line is there's a huge number of opportunities here for participation in ongoing technical development of this. Many of the major subsystems have had a conceptual design already, but there's many subsystems that haven't. Many of the things that have either need new people to step in or collaboration, etc. So there's a tremendous number of opportunities for participation, be it in memory support systems, be it on science calibration systems, etc. So if you happen to have an astronomical instrumentation award for your own, it's kind of interesting. Backstory, just because sometimes MSc has not had a tremendous presence in the US because it's something that, Canada and France started thinking that they should do, but immediately realized that we can't do this by ourselves, we want to bring in a lot more people. So in actual fact, 2010 was when we came up with the idea. This was in response to the decadal plan that goes on in Canada, or the LRP, the long-range plan. And he said we should look into doing this. This is a neat idea, but at the time it was literally, hey, let's knock down this telescope, build a new one, and it can be specialized in this. So people were like, well, that's cool, but can you do it? And so that's what we've been doing ever since. We did a feasibility study to show that what we were talking about was sane, that it was all technically feasible. There was an international workshop held in Hawaii, and that was eventually used to convince the board on the science advisory group's recommendation that they should set up an MSc project office and do this for real. This was when NGCFHC became MSc, and we started forming a much more extended partnership. 2015, 2016, that's when a lot of the science development was done that I described to you, and that then launched into a whole bunch of major conceptual design studies. And in 2017, which I guess now it's just last year, was an incredibly busy year, and we had 10 different major subsystem reviews for 8 different subsystems. We competed to the 5 positioners because it was such a critical and complex thing. Then in January 2018, we had a system-level conceptual design review, where the group came in to look at the entire system as a whole, science requirements and things like this. And then just a few months ago, we basically, this produced an immense amount of documentation, etc., which was useful, but it was not very penetrable to people wanting to find out about the project. So we condensed that into what we call the MSc book. It is on AstroPH, and the first couple of chapters are all of it's highly readable, but the first couple of chapters sort of provide the overall summary before it goes into more detail. So I definitely encourage you to have a look at that if you're interested. And in a couple of months' time, there will be a major meeting held in Tucson, Arizona, which will be a great sort of community discussion about MSc. And then next year on the science side, one of the major things will be the whole further development of the science cases into surveys. The collaboration as it stands just now is a project, officially MSc, the project of CFHT. However, it is not CFHT. We are trying to change not just the telescope, but the entire nature of the partnership. Therefore, we have this thing called the management group, and the board has allowed it, empowered it, to make all decisions regarding to MSc. The partnership formally just now is Australia, Canada, China, France, Hawaii, and India, so CFH, but also Australia, China, and India. Texas A&M, as represented by Darren, and NOAO, as represented by Dave Silva. About 6 months ago, thereabouts became observers in this project, sitting on the management group, and also Jennifer is on the science advisory group as well. And they are essentially discussing if we want to go with this. What's that we do? To give you an idea of the scale, about $10 million nearabouts has been spent on MSc to date, getting into the end of conceptual design. These next 2 years will see us doing a preliminary design phase, for which the total cost estimate is about 25 million. It actually goes down to 20 million, depending on if you include something or not. Of which we've identified about 13 million in terms of in-kind contributions from partners and potential partners. There will be an agreement, a memorandum of understanding, essentially, that will be signed by the group, hopefully with the observers become actual members, that would see us through to the end of preliminary design. You would not see us into the construction. It will be a time limited agreement, clearly, during which time the actual agreement for the detailed final design plus construction will be developed. Okay, in other words, joining now will be part of the discussions to how this thing develops in the future. And the phasing for that is quite nice in terms of here's the timeline and nearly finished. We finished the conceptual design, we released the NRC book, or we had the system level CodeR, which was chaired by Michael Strauss, and had Scott Roberts, who's one of the lead systems engineer for 3MT, Ken Chambers, Ron Sharp, and Herman Scheckler on it, so that was an interesting experience. We had a new call for science team membership. The new detailed science case will be released early next year prior to the meeting that will be held in Tucson, Arizona, which I hope many people will attend. The preliminary design will carry on over the next couple of years, which is very nice timing because that feeds into the Gale Plan in the US, it feeds into the Gale Plan in Canada, a mid-term review of the Australian Gale Plan, and the French 5-year plan called Prospective. And then the design, construction, science operations, etc. And you're looking at about 2026, 2027, more likely, sort of as the technically driven first one. Obviously, that's the sort of optimistic, if everything faces nicely, that's how it works out. Projects never go like that, obviously, except this one. But that gives you an idea of the sort of pacing that we're talking about. Initially, we were managed as a cost cap project, which is to say that the management group several years ago said, what do you think? I think it should cost about 300 million. You like 300 million? Yeah, let's do 300 million. So it became 300 million was supposed to be the cost cap. However, during conceptual design, there was no cost limit imposed. It was a case of design the thing that meets the science requirements, cost it, and then you'll see what we're at. So that was done, and the costing is 270 million based upon conceptual design views. So there needs to be obviously a rationalization of the cost. Like, is this actually a reasonable number? And is this a reasonable number? Or there has to be some reviews going in there. So there has to be this rationalization between the management group and the scope of the project, and now we have a much better understanding of the actual costs. This is the general breakdown. Obviously, you can see that the telescope, just the mirror and just the spectrographs are huge chunks, but there's lots of other things as well that make up big components of this. I think that future looks really rather nice. I do believe that this should be a central part of that future. It's not just me. ESO have identified this last year as something we should be doing. We find such a facility could enable transformation progress. They weren't talking about MSC, obviously. They were talking about their own potential concept for something like MSC. And it would have synergistic impact, and they should be open to considering international partnerships. US reports the NSF support the development of white food hiding in the southern hemisphere. I would say the equator is merely the south, but we can talk about that. Also, again, there's an urgent need to investigate possible development pathways. This is from a more recent report as well. So in other words, we think the international need for this facility is incredibly strong. We think the case for MSC specifically is very well developed. We hope the next few years will be obviously critical for us going forward. We very much hope that Texas A&M is interested. In terms of phasing, I think it makes perfect sense. You can't see the years. This is 2025, this second one here. This is 2030 here. So you can see, SDSS4 becomes SDSS5, 2 meters. The 4 meters we have the most from China. Hermes, which is on the AET. Weave and DESI are about to start up more or less simultaneously. DESI focused very much on cosmology, Weave cosmology, but also other stuff. For most, will come along not soon after. And then on the 8 meter, you have MIND and PFS. And then the sort of timelines for MSE would have it sort of being in the late 2020s. I would say we should be pushing in this. You would really like an MSc set of capabilities at a time when you have LSST-like capabilities. At a time when you have the ELTs and things like this, which depending upon who you believe for the ELTs could be 2024 or 2054 or somewhere in between, definitely in between those two. Obviously it's a big project. And so I think, again, we have a strong case. I think time will be key. If you're interested, please speak to me today. But also, if you go to these URLs, you can get the MSc book, the science case, but there will be a new version very soon. And I very much encourage you to come to this meeting. It's being held and coordinized by NYO as they sort of, they agreed to co-host the meeting, which is very nice. And it'll be a great opportunity to discuss all aspects of this project as it is now, and all aspects of what we want it to be in the future. I'll stop there. Thank you very much.
We have a couple of minutes for questions for Alan.
Great project. Are you at all concerned about the Maunakea lease renewal?
Yes,
33?
absolutely. Concerned and aware, I would say, but yes. So if I can go back here. So this is what's meant, I didn't draw attention to the UH land authorization. So for those who don't know, in 2033, if nothing happens, every single telescope on Maunakea will not be on Maunakea anymore. That's the current expectation. Because there's a mass release, and that mass release allows astronomy to be on the top of the summit of Maunakea. That's a 60-year lease or 70-year lease or whatever. And so discussion now for renewing it is underway. And in fact, the process formally kicked off in February. And the legal process should be a 2-year, fairly well-defined process. At the moment, there's some change in administrative rules that might mean it has to restart. But the timeline for doing that is a 2-year process from the start, and it has already started. And that means nominally, a new lease, which I think, the consensus is that there will probably be a new lease. There will also be conditions, of course. But if that lease is in fact renewed, it's expected to be in the very early 2020s. MSc is not going to build anything on Maunakea. We are a renovation, but we do have to do some construction to the summit. We will not build a thing until the mass release is renewed, for very clear and obvious reasons. Because there's no point building it, going to take it time. If you're renewing the lease, then one of the things that has to go on the table is taking telescopes off. I don't think that will happen. Again, we don't want to be seen to be preempting any judgments. I'm around all day.
I'll ask one. Could you say, so scientifically, the thing I'm most interested in this project is, well, a lot of things, but chemical tag. You mentioned chemical tag briefly. Can you say some more inspirational words about what MSc will enable in the world of chemical
Well, I think inspirational words is a high bar. Right? So let's go with words.
Okay.
And on that, I would say that MSc's attitude to this is very much that this is where I think a lot of the future for understanding the way it's at, not just looking at the way, but specifically looking at. There's some great work out there just now that's being done, even at quite low resolutions. However, the bluest regions are still something that is an area that is not well probed by many existing spectrograms. So that's one of the reasons the MSc turned its attention towards the pure nucleosynthetic enriched part of the spectrum. Which is one of the reasons we're going to report today as well. So I think this field is developing so fast. I think it's still sort of trying to define itself as what it is. I mean that in a great way. It's an exciting state of the field. And so our attitude in sort of 2015, when those specifications were laid down, was let's open up new parameter space. So when you look around at the sort of capabilities, most of the rifle spectroscopy we've done will be a low resolution around 20 K is where it's at. The optical, the windows are like 450 or 500 nanometers or thereabouts. Higher resolution bluer is new, and we know that there's a huge amount of rich stuff there. So MSc's attitude, certainly just until just now, has been to really open up this brand new area of parameter space, as well as opening up this sort of new region of the galaxy, and that's where you can do bulk studies in situ populations. You're actually looking at things out of particular parsecs as opposed to just looking at small populations. Are you inspired?
Yes, very much, thank you. All right, so Alan, as he said, will be around for the rest of today, and I hope many of you get a chance to talk to him. Let's thank him again.
And I'm happy to talk about my science as well.